Hello, everyone, and welcome to our second Calculus 2 lecture. We're talking about the exponential function today. And I mentioned at the end of the previous lecture that we would be talking about the inverse of the natural logarithm function. And that is exactly what the exponential function is. The inverse of f of x equals natural logarithm of x is the exponential function, e to the x. So whenever we see this, we're going to say e to the x. Whenever we're talking to somebody who knows something about math and we say e to the x, they'll know exactly what we mean. Now, I guess the first thing that we need to talk about is what the heck is this thing e? Well, I'll tell you. Depending on who you had for Cal 1, you may have been told in Cal 1 or you may not. But regardless, we're going to talk about e right now. This thing that we call the natural logarithm of x is the same as the logarithm base e of x, where e is approximately equal to 2.718. It turns out that e is a non-terminating, non-repeating decimal. And you're probably scratching your heads now and saying, why would anybody in their right mind choose a number that's not even a whole number? And worse, it's a decimal that doesn't terminate, doesn't repeat. Why would anybody choose a number like that to be the base of a logarithm? If we've worked with logarithms before, that we've probably worked with the logarithm base 10. That makes sense. 10's a whole number. Our number system that we work in is base 10. So why on earth would somebody create a logarithm with a number for its base it's not a whole number, and as a decimal, it doesn't terminate, it doesn't repeat? When I was a student, I thought that I had the answer. It's because all mathematicians are a bunch of flaming jackasses. And this is just something that they did to be cute. I never saw a reason why we'd want a logarithm base e. And if you had me for Calculus 1, I told you what e was. I told you what the natural logarithm of x was. It's logarithm base e of x. And I told you that in Cal 2, we'd come across a justification for why we do something as asinine as this. Have a logarithm with a base that's not a whole number and it doesn't even terminate or repeat. Anyway, this is what the natural logarithm is. The natural logarithm of x is the logarithm base e of x, where e is approximately equal to that number. the exponential function, e to the x, which is the inverse of the natural log function. This function, e to the x, raises the number e to the power of x, where e is this same screwball number, approximately equal to 2.718. Why would somebody make a function like this? Why not have 10 to the x? If you're of the frame of mind that mathematicians just did it because they're a bunch of flaming jackasses, I understand. And at this moment, I'm not going to give you a justification for why we chose this as the base of our exponential function. It's coming. It's coming. And within the week, we'll find out why this choice of a base of a logarithm or base of an exponential function is not quite as asinine as it appears to be. And unlike all the instructors that I had when I was a student, I will actually do you the courtesy of showing you why this is actually not such a stupid idea after all, and why this function, natural logarithm of x, which is logarithm base e of x, really does live up to its name as being the natural logarithm. But for right now, we're going to concentrate on function inverse pairs. The inverse of natural logarithm of x is e to the x. Let's look at some algebraic and arithmetic properties of e to the x. Let's look at the arithmetic properties of the function e to the x. You know what? I gave e to the x the title of f inverse, so let's keep it that way. F inverse will represent the y coordinate here. And this is a graph just so we're clear on this point, this is the same as y equals e to the x. And I'll say this now and I'll tell you again. This is another one of those graphs that we should probably memorize. We should memorize the graph of natural log of x. We should also memorize the graph of its inverse. Let's see what we can deduce from this graph. Notice that over here to the left of the y-axis, the graph gets closer and closer and closer to the x-axis, but it never actually gets there. This graph gets closer and closer and closer to the x-axis, but it never touches the x-axis. And what is the x-axis? Isn't the x-axis the graph of y equals 0? So if this graph never touches the x-axis and never dips below the x-axis, then that means that y, or e to the x, is positive for all values of x. Let's make that our first arithmetic property. Next thing we might want to know is that right here when x is 0, the y value is 1. And from this point, the graph goes upward. So the entire part of the graph of e to the x that lies to the right of the x-axis also lies above y equal 1. This means that if x is greater than 0 over here, then the y value is greater than 1. So we'll say that e to the x is greater than 1 for x greater than 0. So to the right of the y-axis, this graph is greater than 1. And right here at x equals 0, y is 1. E to the 0 is 1. Now that shouldn't shock us. And now notice that to the left of the y-axis, the graph is above the x-axis, but it's below y equal 1. So e to the x is sandwiched in between 0 and 1 for x less than 0. By the way, if we have this graph memorized, all of these points are going to be obvious. Therefore, the graph of y equals e to the x and the graph of y equals natural logarithm of x, it would be a good idea to know what these graphs look like and have them committed to memory. Knowing what these graphs look like will firmly embed all of these properties in our memories. Okay. Now suppose that x goes to positive infinity. As x goes to positive infinity, and as we move along the graph as x goes to positive infinity, what does e to the x, the y coordinate, do? Go to infinity? Yep, like a bat out of you-know-where it goes to infinity. No doubt about this. The limit as x goes to infinity of e to the x is infinity. And if we know what the graph of y equals e to the x looks like, this is going to be pretty obvious to us. One more arithmetic property. Let's let x go in the opposite direction. Let's let x go to negative infinity. And notice, as we move along the graph in such a way that x goes to negative infinity, this graph gets closer and closer and closer to the x-axis, but it never touches it. And remember, the x-axis is y equals 0. So as we move along the graph in such a way that x goes to negative infinity, this graph gets arbitrarily close to the x-axis, which is the same as y equals 0. So the limit of e to the x as x goes to negative infinity is 0. Know these. Don't kind of know them, know them. because it turns out that the exponential function and the natural logarithm function are very important in math and science. Probably more important than trigonometric functions. As a matter of fact, even outside of science, in business, these are very big. And I know when I was an undergrad doing some research, they were also using these in psychology as well. So don't underestimate the importance of these functions. They're important, and if we stay in math and science, or even if we go to psychology or business, we may still run into them. At the very least, they are at least as important as the trigonometric functions. So these are not a passing fancy. They're not the flavor of the week where we're going to taste them once and never see them again. They'll be back. Now let's look at algebraic properties of the exponential function. Okay, algebraic properties of exponential functions. And these turn out to be very useful. But we remember that if f of x is the natural logarithm of x, then f inverse of x is e to the x. They're inverses of one another. And since they're inverses of one another, f evaluated at its inverse, f inverse of x, is just going to give us x. Whatever f inverse does to x, f undoes it, and vice versa. Now, what exactly is f evaluated at f inverse? Let's see. F evaluated at f inverse of x. Let's notice something. This is our model of f of x. F of x equals natural logarithm of x. Down here, we have f evaluated at f inverse of x. So down here, f inverse of x plays the role that x plays up here in our model of f of x. So every place that we see an x up here in our model of f of x, we're going to put f inverse of x down here. So f evaluated at f inverse of x is going to be natural logarithm evaluated not at x, but of f inverse of x. And note that's because down here, f inverse of x is playing the role that x plays up here in our model of f of x. So every place we see an x up here in our model of f of x, we put f inverse down here. And then to figure out what this actually turns out to be, we realize that f inverse of x is the same as e to the x, so we make that substitution. We'll substitute e to the x for f inverse of x and get natural logarithm of e to the x. Well, what does this turn out to be? This is the same thing as f evaluated at f inverse of x, which is x. So this thing is just equal to x. This is how the natural logarithm of x undoes e to the x through function composition. Natural logarithm evaluated at e to the x is just x. And this is a consequence of the two being inverses of one another. Now let's look at something else very closely related to what we just did. We're going to turn the tables and we're going to evaluate f inverse at f of x. And what I didn't do right here is just note that since these two things are inverses, when we compose them together, we just get x. F inverse undoes whatever it is that f does to x, and we just get x. Okay. As a consequence, this should be f inverse evaluated at f of x. We have f inverse evaluated at f of x. And notice that f of x plays the role down here that x plays up here in our definition of f inverse. This is f inverse evaluated at x. This is f inverse evaluated at f of x. So down here, f of x is playing the role that x plays up here in our model of f inverse of x. Therefore, every place that we see an x up here in our model, we're going to put f of x down here. So instead of having e to the power of x, like we do up here, we're going to have e to the power of f of x. Because down here, f of x is playing the role that that x plays up here in our model of f inverse. So we have e raised to the power of f of x. And f of x is the same thing as natural logarithm of x. And we'll make that substitution, e to the power of natural logarithm of x. And what the heck is this equal to? Well, notice e raised to the power of natural log of x is f inverse evaluated at f of x, which is equal to x. So we've just established that e raised to the power of natural logarithm of x is equal to x. This is how the exponential function undoes the natural logarithm function through function composition. Now, out of all of this, here's what we want to focus on. Everything else that we did up here was just justification to validate these two algebraic properties of the exponential function. So from everything that we have up here on the board right now, what we're going to take away primarily is this fact and this fact. Those will be our two cornerstone properties of the exponential function. Fundamental algebraic properties of the exponential function. E raised to the power of natural logarithm of x equals x. They undo each other. E to the x and natural logarithm of x. And natural logarithm evaluated at e to the x equals x. They undo each other through function composition. And the typical laws for exponents hold for the exponential function. e to the x plus y is the same as e to the x times e to the y. E to the x minus y is the same as e to the x over e to the y. E to the x raised to the power of n, the exponents multiply. And maybe I'll add one more. E to the negative x, 1 over e to the positive x. Properties 3 through 6 are just the general properties of exponents that also apply to the exponential function e to the x. And should we know these? Yeah, we should. If we continue in math, 1 and 2 are going to be extremely important when we take differential equations. They're also going to be important on our Friday afternoon quizzes because very soon they will be formulas that we should know. So these aren't going away. Memorize them. And I think now might be a good time to end this lecture. Oops. You know, I wanted to say something during the previous lecture and I forgot, and I told myself I was going to mention it in this lecture, and I forgot. But I just want to mention this because we should know. I've talked about functions having inverses, and we may be under the impression that every function has an inverse. And that's not true. Some functions do have inverses, but some functions don't have inverses. And those functions that do have inverses, they come in pairs. Each one is the inverse of the other. But I just wanted to dispel any notions that we might have that every single function that there is has an inverse. That's not the case. So we will stop here for lecture number 2. And our next lecture, we will talk about the calculus of exponential functions. And I think you'll find that the exponential function e to the x has a rather amazing quality when it comes to differentiation. So that's something to look forward to.